All right, welcome back. Just getting started here with this live stream. Think we are good to go. Okay, let me just confirm that. I think yes, this seems fine. Okay, so today we are going to be doing a counting problem, and we'll see how far we get. Okay, so I may be I will certainly be gobbling up a few details, uh, but again, hopefully some of the main ideas come through, and hopefully you find this to be an interesting question as well. Whatever we're going to do might remind you of things like integer partitions and so forth, but I'm going to skip all of this very nice context and get straight to the problem, which is at the heart of human nature. So we are today asking ourselves, in how many ways can we build a wall inside this bounded region if we are given k bricks, and we are interested in non-increasing walls. So if you want to, really be precise about what we mean by a wall here, you could think of it as a sequence of numbers which are, well, non-decreasing, and they sum to k. Right, so that's what we are looking at. So for instance, here I think k is 10, and the sequence we are looking at is 3, 2, 2, 1, 1, 1. So as you might have guessed, that's one way of writing 10 as a sum of a bunch of numbers. As you can see, we are allowing for repetitions, but it's sort of an ordered sum in that we want sort of the tallest or the largest number to come first, and so on. So it's ordered in non-decreasing order of summons, right? So we are going to let PWHK denote the number of non-increasing walls we can build within a box of height h and width w. So if you prefer the summons way of talking about walls, then the bounded box is basically telling us that we are trying to write k as a sum of a certain number of terms, where the number of terms does not exceed w, because that's how many we can afford to fit in here. And each of the summons, the magnitude is bounded by h. So I want to write 10 as a sum of few things, but I'm not allowed to say something like 9 plus 1, for instance. The reason for that is 9 would overshoot the boundary of my bounded box on the height end. And I could also say something like 10 is 1 plus 1 plus 1 on and on 10 times, but that's also not allowed because then I would overshoot this on the width end. So this is only 8 columns long. So those ways of writing 10 as a sum of numbers are basically thrown out. So the only valid ones would be ones where I've used at most 8 terms, and each of the terms is at most 4 in magnitude. And we're interested, for whatever reason, in counting the number of ways we can do this. Actually, we won't actually count the number of ways in which we can do this. I don't even know if there is a nice closed form for this, but what we are going to show is the relative relationship between PWHK and PWHL for k less than L. But is the quantity PWH of k, is that clear? Is it clear what it's counting? Give me a +1 in the chat if the definition makes sense. All right, awesome, thanks. So I didn't hear any questions or complaints, so I'll just move on to telling you about what we want to try and show. So here's the main theorem in this miniature, which says that basically the PWHs across K, so you can, the valid range for K is between 0 and WH inclusive. Either you have no bricks, that's one extreme, and the high end of it is that you have all the bricks that you can ask for, W times H, width times height, anymore, and it doesn't make sense because you wouldn't even be able to use all of them. So the number of bricks varies between 0 and WH, and if you look at PWH as a function, so think of W and H as being fixed. You have a fixed bounded box that you're working with. And if you think of this as a function of k, where k takes these values, this is what you would call a unimodal function. At least that's what the miniature also reminds us. Essentially, this is to say that these values go up, peak, and then come back down. Okay, so that's it's kind of the idea. So you can see that the values are rising here, and then they're going to fall. And here at the extremes, maybe this is worth doing easily. I think there's only way that you can build a wall with no bricks and all the bricks. Is no two different ways of doing this. That's going to be the same, I think, with one brick. Although with one brick, you have a lot of places where you can put that brick, right? However, for a wall, that brick has to first of all be on the ground because gravity. And because we're only interested in non-increasing walls, this brick has to occupy the bottom left corner. And for the same reason, the missing brick here has to occupy the top right corner. So there's only one way of doing these things. But as you go along, it gets more complicated. So that's all that I will say. These are really the very, very trivial extremes. But the idea is that the number of ways in which you can do things, you start having more flexibility. I don't know if it's worth doing just for 2 or 3 maybe. I think I do have an interactive thing coming up in a couple of slides. So we'll try it there if somebody reminds me. Okay, but this is what we want to show. And before we try to establish this unimodal thing, let's actually win half of the battle by pointing out that if we can show that it's increasing up to the halfway mark, or at least non-decreasing up to the halfway mark, then it's non-increasing beyond the halfway mark. And I don't know if anybody has any guesses on why this is true. One of the things is we are going to try and relate these quantities like we just saw. Well, these all turned out to be the same. But in general, if you have a quantity in the middle here, can you relate it and say that it's equal to some quantity on this side? And can you do it in a way that this implication goes through? So we are thinking about the number of ways in which you can build a wall with k bricks, where k is at most half the total space that we have. If the number of bricks is at most half of the total space that we have, what can we say about the white space, which is all the locations where there are going to be no bricks? If the number of occupied locations is at most half, the number of unoccupied locations is, can we say something about that? Is it at least half, exactly half, also at most half? So the number of bricks is K, and the number of non-bricks or empty locations is WH minus K. Yes, so Krishna has beaten me to it by quite a mile. So so I was going to say that if the number of bricks that you have is K, then the number of empty locations is WH minus K, which means that if you're working with at most half the bricks, then you have white space material that's at least half. So now if you just flip around, okay, let me maybe just show you the picture, which should make things a lot clearer. So we want to claim that the number of ways of working with K bricks is the same as the number of ways of working with WH minus K bricks. And that's because you can simply imagine knocking out all the bricks and bringing bricks wherever the non-bricks were originally. And then if you just, either tilt your head or rotate this figure, then you have a valid wall built out of all of the non-bricks. And that's exactly what Krishna said. And Jayati, indeed, the question that I was asking earlier, if you have at most half the bricks, then you have at least half non-bricks. And now if you switch their roles, then you go from a wall of K bricks to a wall of WH minus K bricks, except this wall is like a valid wall in outer space or something. So to make it a valid wall in our world, you'll have to turn things around, but that's an easy operation to do. So is this implication fair? Are we happy with just proving one half of this theorem because the other half we get for free? Awesome. All right. So now we focus on the first half, and just a little bit of notation up front. So we're going to imagine that this bounded region has n boxes. 1 to n. Unfortunately, I was hoping that they would be indexed ij or something, but we're just going to use numbers from 1 to n. Actually, I don't think these numbers come up very explicitly, so I don't have to be so sad about this. N is just the total number of squares, and it's w times h. And this is what we said we will prove. So worth remembering that we're always going to be working with K and L. So working with K bricks versus L bricks, and L is strictly more than K, and both of these are in the range 0 to n by 2. So you're working with at most half the bricks at any point of time. And we want to say that there are at least as many ways of building walls with more bricks as there are with fewer bricks at hand, if you're in the at most n by 2 regime, right? Okay, so first what we are going to do is we are apparently going to be working with the space of k-sized subsets of n, and we are going to the n choose k of those. But if I pick a random subset of, k locations in this bounded region, that's not going to look like a wall. So we are going to try and partition the n choose k space into PWH of k many parts, where for each way, for each subset of locations that you give me, I'm going to think of them as bricks that can be morphed into the kind of walls that we're working with. So suppose you give me the subset. This is clearly not a wall of the sort that we were looking for. There's, first of all, some bricks suspended in mid-air. And the other issue is that, it's not clear that it's a non-increasing collection when you look at it column-wise. So to transform this systematically into a non-increasing wall, a valid wall-like structure, first we are going to let gravity do its thing. So let all the bricks drop to the ground, right? And now we're just going to reorganize the columns so that, you have them in non-increasing order. So I was really just thinking of this as a multi-set. I don't know if that's not a valid way to look at it, but really just an ordered multi-set. So here, for instance, this multi-set would be 3, 2, 2, 1, 1, 1. That's just the number of bricks per column. And if you want to be, I guess, complete, you also get 0 twice. So yeah, any multi-set also kind of corresponds to a wall. And so this is what we have here. So you could basically go and count the number of bricks that you see in each column, and that already gives you the elements of the multi-set. So I can record from here a 1, 0, 0, 3, 2, 1, 2, and 1. But now I just rewrite that in non-increasing order. And I now have my wall. That's basically what this transformation is doing. And yeah, I was not sure if this transformation would be clear or not. So I have, this is now interactive. We can work with a different example if we want. Okay, maybe let's knock out whatever is on the ground. Okay, so if I had to transform this into a wall now, can somebody just describe this maybe as a multi-set? Just to make sure that we're on the same page. Let's see if I can work through it. So we'll make another copy here. And yeah, it's a little bit like 2048. You're right. Yeah, except we don't have things colliding and merging. But yeah, the falling part of it is a lot like the 2048 mechanics, right? I don't know if you've checked out there's a PhD version of 2048, by the way, which is a lot of fun. So each of the boxes in the PhD version of it represent different stages of doing a PhD, and they collide to make progress, apparently. But yeah, it's a slightly depressing vision. But okay, so yeah, do look that up. It's fun. Oh, I had a layer of these. I could have moved them around. How silly of me. Okay, all right. So this is the version where gravity has done its thing. But now if I want to really get to the wall associated with that subset, I still have to move the columns around. So I'm going to pull these out, right, and put them right there at the end. And I think that should almost do it. You zoom out of it. Maybe throw this away. Okay. All right. So is this transformation process clear in terms of what's going on? Yeah. Okay. All right. So yeah, gravity down followed by a pull for the heavier objects towards the left. Exactly. So so first within a column things fall down, and then across the columns get rearranged so that you get to a valid wall. So now the idea with the equivalence class is to say that, whoops, okay, I'm afraid I jumped ahead a little bit. Okay. Yeah, all right. So basically, like we said, we are going to be looking at the space of all k-sized subsets of n, and two k-sized subsets of n are said to be in the same equivalence class, or said to be equivalent if when you do these operations on those two subsets, you end up with the same wall. Okay, and it's not hard to check that this is a valid equivalence relation, meaning that it's symmetric, reflexive, and transitive. I think all of those things work out pretty much by definition. So what you get is actually a partition of this n-choose k space into PWH of k many parts. Okay, so this concept of an equivalence relation and equivalence class here. Okay, give me a +1 if it makes sense. Yeah, I'm sorry, maybe I've already asked that before, but okay. Yeah. All right. Thank you. Yes. So now we're just going to restate this definition in more professional sounding terms. And in fact, even Mathuchek in the footnote says that there's even a more well, I mean, basically, you can think of this in terms of a subgroup of the permutation group or something like this, and the equivalence classes turn out to be orbits or something. But he says in the footnote that he doesn't want to scare people off, so he's going to refrain from using that terminology, and I'm very much on board with that. So, but nevertheless, I think let's just talk about this alternate view, which is only used in the proof of a lemma where I'm not even sure if I want to necessarily invoke this definition, but it's still good to maybe see this alternate formulation. So essentially think of, okay, so we have this numbering, right, from 1 to n. Now I didn't want to write 1, 2, 3, and so on. So instead of numbers, I have colors here. And as you can see, what we have here is a permutation of the colors, right? So the final permutation is the one that you see on the top, on the bottom. And what you see on the top is what I'm thinking of as the identity permutation. So think of that as 1, 2, 3 up to n, the original labeling, which is some arbitrary but fixed labeling of the boxes, right? And I've messed around with the colors a little bit, but notice that it's not a totally chaotic permutation of the colors. Okay, so the way it's obtained is by saying that, okay, I can mess around with the colors column wise. Okay, so I can rearrange. So you'll see that in the first step, I've only moved things around within a column. So for instance, I don't know, has anything even happened? Yeah, I suppose the light orange has moved down, the dark blue has come up and stuff like that, right? So all the rearrangements have happened within a column. And now I've taken these columns and I have swapped some of them, I've moved them around, but as columns, right? So in some sense, if you look at this permutation, it has moved things around, but in a somewhat restricted way, right? So we never have like, things spilling over across columns. So, all the blues stick together in one column, all the greens stick together in one column, and so on. The columns themselves may have moved around, and things within a column may have been rearranged quite a lot. But that's about it. So these permutations are called or we are going to just call them non-column breaking permutations for obvious reasons, I suppose. And now the idea is that if you give me two subsets, right, then it turns out that they belong to the same equivalence class in the way that we have described, if we can find a column breaking permutation that transforms one subset to another. So, well, I think it's clear that there is a common third subset K triple prime, which is the subset corresponding to the wall. And there is a permutation that takes both K and K prime to that K, I don't know why I said triple prime, K double prime, right? So K double prime is that wall that both K and K prime transform to, because that's why they're equivalent. And certainly there is a non-column breaking permutation that would take K to that K double prime and K prime to K double prime. And my guess is that you can basically combine, you can take the action of the first permutation and I think the inverse of the second permutation, played back in reverse, to directly go from K prime to K. So basically, K prime is some arbitrary subset with some bricks hanging midair potentially and weird stuff happening. And K is a different subset, which also looks all kinds of weird. And the idea is that we have a non-column breaking permutation that can morph one of these subsets to the other, if and only if both of these lead to the same wall when we do the gravity thing twice. Okay. And I don't know, I hope this at least sounds superficially convincing. I think you can work it out. I worked out a few small examples, and I think it makes sense that the pi comes as a composition of two natural permutations. The first permutation is the one that takes K to the wall, right? And then basically it's like you have a permutation that takes K prime to the wall, run that in reverse. So the inverse of that permutation composed with the proper permutation for K, that will take K to K prime. Does that make sense? Okay, I suppose at a high level, what's happening is that this idea of a non-column breaking permutation is basically just a little bit of language to capture this 2 times gravity action. That's more or less what's happening. I think it's not going to be terribly important to our later discussions, but if something is particularly confusing about the mechanics, then do let me know. If I'll wait for like 30 seconds for any questions in the chat, or feel free to unmute yourselves. Oh, unfortunately, I didn't realize that I had my volume all the way down. So if anybody said anything earlier, I may not have heard you. I'm sorry. But I mean, welcome to unmute yourself if you wanted to say something. Okay, so if we have wall equivalence and if wall equivalence is clear, you don't have to worry a whole lot about this idea that any two subsets that are wall equivalent are related by a non-column breaking permutation. That's the claim that's being made here. By the way, I guess it's not completely clear, this notation also, pi of K, because K is a subset of locations. I guess it's a subset of n. So what does pi acting on a subset mean? I don't know if that's standard notation, but I'm taking it to mean that pi acting on this subset basically means that it moves things around in this subset in a particular way, and I think the other stuff basically readjusts to. So for instance, pi could be the permutation that essentially, let's say, swaps a couple of locations and it's fixed everywhere else, for example. So for me, I was a little thrown off also by the notation pi acting on a subset, but I suppose that's clear to people who work with permutations and especially think of it as a group action or something like that. But I have a very sort of hand-wavy mental image of what this might mean. I think the reason that this definition is introduced is so that they can knock out one of their technical lemmas with a two-liner. And to be honest, I wasn't sure that I was confident in how I parsed the two-liner, so I'm just going to anyway describe that lemma at an intuitive level. So let's just maybe, not worry about this definition too much if it's not completely clear. But are there any other questions, or can we move on in trying to get to the main proof? So just give me a +1 if you're happy to move on, or if you have any comments, then this would be a good time. Okay, cool, thanks. All right, so remember that K is the one that's the smaller of the two between K and L, and both of these fellows are between 0 and n/2. That's our setup. And we have these equivalence classes coming from, the set of K bricks, that's K1 through Kr, and the number of equivalence classes. Remember, each equivalence class you can think of, so PWH of K is all the different non-increasing walls that we can build with K bricks. And so each of those walls can be thought of as sort of a representative element, because those walls also are K-size subsets of N. So you can think of those as being the representative elements of their class. And so there are clearly R of these classes, and they're exactly R classes, right? So, okay, and now you can do the same for L, right? So you can take the L element subsets, sing the same song, and do the same dance and say, okay, the L-sized subset space also gets partitioned into some S parts, where S is PWH of L now, which is the number of non-increasing walls that you can build with L bricks, right? So we have K1 through Kr, which are the equivalence classes of the N-choose K space, and we have L1 through Ls, which are the equivalence classes of the N-choose L space. Okay, so these are the two sets of equivalence classes that we have. And of course, we want to prove that R is at most S. So the number of paths we get using K bricks is at most the number of paths we get using L bricks, which is more bricks, right? Okay. All right, so now we are going to reformulate this as a graph where the vertex set is basically all K-size subsets, all L-size subsets, and then you have edges based on inclusion. So this is, you might have seen this when you see the Hasse diagram, but in the Hasse diagram, typically you see the edges between two consecutive layers. So typically you're seeing edges between I-sized subsets and I+1 size subsets. Now you could be at some intermediate layer, which is the space of all K-size subsets, and then some layer that's above it could be the one that's immediately above it. It's possible that L is K+1, but it could also be further up, although no further up than n/2. n/2 is our ceiling, right? So basically we have these two. Okay, so this is an image from the book. So here, for instance, we have, I don't know if this is all of them or not, I suspect not, but this is on the bottom you see all of the 3-size subsets of a 6-size set. So N is 6 and K is 3, right? And on the top you see all the 2-sized subsets of a 6-sized set. So N is of course fixed across the board, and it's again 6, but now we are only using 2 bricks instead of 3, right? And if you focus on any one of these edges, it'll turn out that, for instance, you can think of it either way. You can think of this as being obtained from this by knocking out one of the squares, or you can think of this guy coming from the one on the top by adding one square somewhere. So both of them are valid ways of interpreting these edges, okay? And I just want to spend a minute thinking about, well, okay, so let's maybe zoom in a little bit into this picture, because there's lots going on here in terms of lots of edges and so on. So let's say that this is one of our elements. So this is from the top layer where you're looking at 2-size subsets. Let's ask ourselves, how many neighbors does this guy have in the bipartite graph? So this will be adjacent to all 3-sized supersets of this 2-sized subset. So how many of those are there? So I know that these 2 bricks I have to hang on to because I'm looking at supersets. The adjacencies are based on inclusion. But I get to, because L is 3, so K is 2 and L is 3. I get to add one more brick. And in how many ways can I add one more brick to what I already have? And there are no constraints at the moment. These are all, arbitrary subsets. So we don't have to maintain being a wall or having respected gravity or any of that. So with no constraints, in how many ways can we add one more brick to this collection of 2 bricks to get 3 bricks? There are exactly 4 possible ways, absolutely. So, so you could either take the top left corner, the top right one, or this one or this one. Yeah, so there are 4 ways of doing it. So the degree of this vertex is 4. In general, if you had some k-sized subset here, and you were trying to figure out what are all the L-sized subsets I'm adjacent to, well, these k elements are fixed. And from the remaining n minus k spots, we are trying to pick L minus k bricks, right? So you will have n minus k choose L minus k degree in general. Does that make sense? In this case, n minus k is 6 minus 2, 4, and L minus k is 3 minus 2, 1. So 4 choose 1 is 4. Yeah, okay. All right, very nice. So these, these degrees vary based on, okay, so let's see. In fact, I guess all of these guys would end up having the same degree because of what we just said. Yeah, okay. So, but now we want to say, okay, so the degree is in some sense uniform across the board, but we want to also look at the degrees going into these equivalence classes and argue that those degrees are also uniform in some sense. Okay, so let me look at 2 things which are in the same equivalence class on the, well, this would be, maybe I should have, this is probably not going to be consistent with the notation here. So, okay, so L is the thing with 3 bricks, right? So that's fine. So these 2 images here of, a collection of 3 bricks, these are 2 things from among the LIs, right? And I claim that these 2 are in the same equivalence class because if you did the gravity thing, this would go down, this would go down. And in both cases, you would get the wall, which has 2 bricks on the first column and 1 brick on the second column. So these 2 guys come from the same equivalence class, Li. It's some Li, okay? And now I want to say, well, fix any 2 objects in a common equivalence class Li. And let's ask ourselves, how many things do they see in some equivalence class Ki, right? And this was the thing that was knocked out with a one-liner in the miniature based on this pi definition. So saying that, oh, you just apply these non-column breaking permutations to get to Ki or something. But even intuitively, so I want to claim that both of these have the same degree into have the same number of neighbors here. And I think the reason I felt this is intuitive is because really we are thinking of these as multisets, right? Being the same multiset. So both of these guys are the same multiset, in this case 2, 1. And in Ki, what we are saying is that, well, they are also the same multiset. But now the sum is 1 less, right? So because K is a smaller thing. So in general, the sum is K minus L less now. And in some sense, we're saying, well, in how many ways can we morph, one multiset into another one? And my point is that this is basically independent of the, of the individual. So the point about these 2 things being in the same equivalence class is that as ordered multisets, they're exactly the same. So you look at the common ordered multiset that these guys correspond to. So in this case, that would just be 2, 1. Right. And here also, all of the KIs have this thing that they are a common multiset. So possibly this is 1, 1 or something, because the Ks have, 2 bricks. It could also be something like, say, 2, 0, for instance, right? So now basically, the adjacencies here, I mean, essentially if you look at the representative guy, the only way to go from a 2-1 to a 2-0 would be to basically knock out the one brick in the column that has just the one brick, right? And so essentially that it's the same mechanism for each of the elements of this equivalence class to morph into something that's an element of the equivalence class that's down below, right? So if I have to go from a 2-1 to a 2-0, I know that there is only one way of doing that, which is to take the columns that, in this case, the column that has the one brick, and to turn that into a column that has 0 bricks, right? So in a more general thing, I mean, maybe we could try a more general example where we say 3, 2, 1, 1, 0, 0, or something like this. And now we are trying to morph this into, let's say, something much smaller. So 1, 1, 1, 0, 0, 0, right? And now basically I know that the only way I can do this is if whatever column had 3 bricks loses 2 of them, whatever column had 2 bricks loses 1 of them, right? And whatever column had this one brick, that also would have to lose it, and this column stays unchanged. And the point is, if you look at different elements of the Li, they have these 3, 2, 1, 1, 0, 0 manifesting in different ways. They may be in different orders. Within a column, these 2 bricks could be at different places. But the point is that when I look at the column which has 2 bricks, I know that it has to lose one of them. And the number of ways in which 2 bricks can become one brick is the same, irrespective of where that column is. So at least intuitively, is it clear that, if you're looking at 2 elements in a common equivalence class on the L side, and you're fixing an equivalence class on the K side, right? Then any 2 elements in Li will have the same number of neighbors in Ki. That's what we are claiming. So is this a reasonable claim? Can you give me a +1 if it broadly makes sense? Yeah, okay. All right. Like I said, it's a one-liner or a whatever, one long liner in the miniature. And this is, I think, the only place where the column preserving, non-column breaking permutation definition is used. So if that's your preference, you can go and look at exactly how that's done. But I felt that this was independently quite intuitive. So this is, now this is what we are going to call a homogeneous partition. So in general, if we have a bipartite graph, which we did, which is each side is partitioned into a number of parts, what we have is, we said that if you look at any, what did we say previously? If you look at any Li, and if you look at all the vertices in Li, they have the same degree. And if you look at any Lj, they all have the same degree into any of the Kis, right? I mean, so fix a Ki and all Lis will have some, Dji degree into Ki, right? This is what we want to say. So this is what is called sort of a degree homogeneous partition. So here, let's say that you have, now I'm saying this in general terms just to match the presentation in the miniature as well. So let's say you have a bipartite graph with parts U and V. Let's say U has been partitioned into some R parts and V has been partitioned into some S parts, right? We say that this is V degree homogeneous if you fix any Vj you like, and all the vertices in Vj have the same degree into any of the parts on the top. So fix a Ui on top, all the vertices in Vj have the same degree into Ui, and that common degree we are going to call Dij. Okay. All right. So now remember, we want to say something like, R is at most S. This was our goal. We have the larger set. So V is basically for us, it's representing the bigger sets, and U is representing the smaller sets. So U is the K-sized subsets that give us, R parts, and V is all the L-sized subsets that give us S parts. And we already know by what we just argued that when we look at that, the graph that we had built, that's actually a V degree homogeneous partitioned bipartite graph, right? And we want to say that, well, if that's the case, that's what we have to go by, then R is at most S. And it turns out, well, I mean, I wish I could say that this is always true for, these bipartite graphs. It's not always true, but it is true if you look at the bipartite adjacency matrix of this graph, and the rows happen to be linearly independent. So this bipartite incidence graph, you'll recall from yesterday, is, well, the rows are indexed by U in this context. The rows are indexed by U, the columns are indexed by V, and you have an edge if the vertex represented by row I and the vertex represented by column J, if those two are adjacent in the graph. So that's the bipartite adjacency matrix. And it turns out that if this bipartite adjacency matrix has the property that the rows are linearly independent, then R is at most S. Okay, provided that the graph is V homogeneous to begin with, that you have this property that all the vertices in each of the V parts have the same degree into each of the U parts. You do need that. Now, I'm not going to prove this lemma, although it's not a very, I mean, I think we've seen a lot of miniatures where we have tried to argue things. Well, we have tried to establish linear independence and then take advantage of this. And here, what we are saying is that if we are given that the rows are linearly independent, then R is at most S. Notice that R is not the number of rows in the matrix. This is R is the number of parts that the rows can be partitioned into. And S is the number of parts that the columns can be partitioned into, so that you have this degree homogeneity condition, right? So I'm going to leave this as something that's quite doable. I think, in fact, the proof that we are going to see, even though probably briefly, the proof that we are going to see is an argument is a calculation in a very similar spirit. So it's this lemma, after we go through the other proof, might even be something that's like nice to just try and work out on your own, potentially as an exercise. Or of course, the proof is there in the miniature, so you can go and look it up there. But is the statement clear? You write down the bipartite adjacency matrix of this graph here, and if the rows turn out to be linearly independent, then the number of parts on the row side is at most the number of parts on the column side. That's what we get. And maybe just as a sanity check, how do you think we can apply this lemma to get what we want? What do we have to show next now? We do have a bipartite graph, a partitioned bipartite graph that comes out of our setting. What do we need to show about it to get the result that we wanted? The result that we wanted is that, notationally it was that R is at most S. So the number of parts that we get out of using K bricks is at most the number of parts we get using L bricks. So for us, V was like L, where it was all the L-sized subsets, and U was like K, all the K-sized subsets. So this is on top we have the n-choose K space, and the bottom we have the n-choose L space. And the n-choose K space, the wall equivalence partitions it into R parts, and the n-choose L space, the wall equivalence partitions it into S parts. Therefore, R is the number of walls we can build using K bricks. S is the number of walls we can build using L bricks. And we wanted to say that S is at least R, right? So what we want to show seems to, well, this lemma seems to give us the conclusion that we want. So if we know that our graph satisfies the premise of the lemma, then we are done. And in the premise of the lemma, we have a couple of things. One is that it's V homogeneous, which we already showed. So what is the other thing that we now have to show? Like, what remains to be done? If you believe the lemma, then what remains to be done? Yeah, exactly. We need to show that the rows of our matrix, our specific matrix that comes out of our specific bipartite graph are linearly independent. If we can show that, then we are in business. This lemma takes care of the rest of it for us, right? So what is this matrix whose rows we are trying to show linear independence for? So yeah, thanks for that answer, Radish. That's perfect. So here's what, okay, so maybe I'll just skip ahead and show you a snippet of the kind of matrix that we are looking at. So our matrix was coming from this bipartite graph that I showed you only very briefly. This one here. So this is the bipartite graph that we are working with. On the V side, we have all the L-sized subsets. On the U side, we have all the K-sized subsets. The incidences come from containment, and the partitions come from this wall equivalence relation. So given that the partitions come from the wall equivalence relation, we already know that we have a V homogeneous partitioned bipartite graph. So if we can show that the bipartite adjacency matrix for this particular graph has the property that the rows are linearly independent, then we apply the lemma and then boom, we are done, right? So does the plan of action make sense? So we are only left with showing that our specific bipartite graph leads to an adjacency matrix whose rows are linearly independent. Once we do that, we can apply this lemma to get the consequence that we wanted. Yeah, so give me a +1 if the plan makes sense, and then I'll move on. Yeah, thanks. I think you'd already come up with that. Can anybody else confirm that this is still making sense? Okay, so let me just recap what I said we will prove. So the graph that we were looking at basically had one side where the vertices were K-sized subsets of n. The other side was L-sized subsets of n. And you had a relationship based on set containment, right? So if you translate that graph to a bipartite adjacency matrix, you will have, let's say, rows indexed by the chota sets, the K-sized sets, and the columns indexed by the larger sets, which is the L-sized sets, okay? And again, you have a 1 between I and a j if you have containment. I couldn't pull out, I couldn't make the whole thing fit, but here is an example with, I think what was the example in the miniature. So you have 2-sized subsets of 1 to 6 on the one hand, and 3-sized subsets of 1 to 6 on the other. So the rows are 2-sized subsets, the columns are 3-sized subsets. And hopefully, again, if I've not made mistakes, the matrix should make sense. So for instance, if you have a 1, 6, and then you have a 1, 3, 6, that should be a 1. And 1, 2, 6 is also a 1. So whenever you have containment, you have a 1 and you have a 0 otherwise. So is the matrix that we are dealing with clear? The rows are indexed. There are n choose k rows and n choose l columns. And hopefully the semantics of the ones are okay. Yeah, okay, awesome. So this is the matrix that we are working with, and we've already done all the work in terms of what is R and S, right? So we said, well, look at the wall equivalence relation that will give you R paths on the row side. It'll give you S paths on the column side. I hope I didn't mix that up, but yeah, I think that's what it is. And yeah, so the smaller sets have R, the bigger sets have S. That's what we set up the notation to be. So PWH of K, we said, is R, PWH of L is S. And so the wall equivalence relation gives you R parts on the row side and S parts on the column side. And we have already argued that this is a homogeneous partition, meaning that if you looked at so from the wall equivalence point of view, if you looked at two things in the two L-sized subsets, and you ask them how many neighbors do you have in any of the KIs. So two equivalent L-sized subsets. and you ask them, well, how many neighbors do you have into one of the equivalence classes on the K side, they will both report the same number. So this is something that we argued by talking about the multisets and all of that, right? So this is already a homogeneous setting with respect to the equivalence class partitions that we have seen. So to apply the lemma and get that R is at most S, all we need is to show that these rows are linearly independent. If we can show that, then we are in business. And that's what we're going to show next. Okay, so and this will be the last thing. So we're going to try and find, yeah, I don't know if there's anything else that I wanted to emphasize. No, I think this is good. Let's just, yeah, I just wanted to confirm that once you have this, you can really apply the lemma and get the consequence that you want. Okay, all right, so we're going to try and yeah, prove this by contradiction, trying to find a non-zero vector y such that when you apply, I don't know how best to say this, but y transpose B is 0 and the matrix acts on y, but from the other side, then it's 0. So is it clear how many entries y should have? So B is n choose k column, n choose k rows. And n choose L columns. So y transpose B is 0, which means what's the dimension of y? This is the 0 vector again. Right, it's n choose k, right? So it's acting from the left, and so we need to be able to, yeah, we need to have y interacting with each of our columns one by one, and that's going to mean that y has n choose k entries. So think of y as being indexed by all the k-sized subsets of n. Okay, so it's a long vector, and we know that it's a non-zero vector, so there must be some subset, some k-sized subset for which y indexed at that subset is non-zero. So let's just call that k naught, which is a bit ironic, but at k naught, y is non-zero. Okay, so that's, we're going to fix this. And now, I don't know, this is a bit annoying. We are reusing ki and lj to mean something completely different now. So this is because the homogeneous business is done. We can totally forget about it. And now we are looking at a different partition of n choose k and n choose L, that space, based on the sizes of the intersections with k naught. So k naught is this, think of k naught as some arbitrary but fixed subset of size k. It's important because that's the index at which y is guaranteed to be non-zero, and this will somehow be useful later. But now let's think of the space of all n choose k subsets being partitioned into k parts based on, what is the intersection, what is the size of the intersection between k and k naught. Okay, so maybe that wasn't useful. Let me just see if maybe we can do an example here. Yeah, so let's say y was non-zero at 1, 2. So let's say this is k naught. Then this whole space of two-sized subsets is going to get partitioned into 0, 1, 2. So basically 3 parts based on how much you overlap with k naught. So the only person who overlaps with k naught at 2 elements is k naught itself. Nobody else overlaps with k naught at 2 elements. So that equivalence class, or that, I shouldn't call it an equivalence class anymore, that part of the partition, k sub 2, has just this element. Who are the fellows in k sub 1? In k sub 1, we have all those subsets which overlap with 1, 2 at exactly 1 element. Okay, so that would be, I think, all of these guys and all of these guys, right? So these are all in K1 because their intersection with K naught is exactly 1, right? And what can we say about all of these guys here? Where do these guys belong? So remember, we took the space of all subsets.
K0.
K0. Yeah, right. Thanks. So this would be K0. So we said K0, K1, K2, based on how much they overlap with K naught. And these are all fancy Ks. And K naught has the normal K. So K naught here is 1, 2. So let me not make K naught explicit. But, overlap, if you overlap with 1, 2 at 2 elements, the only way you can do that is if you're 1, 2 yourself, then you go into K2. If you overlap with 1, 2 at exactly one element, which is either 1 or 2, then you go into K1. And if you don't overlap with 1, 2 at all, then like the last 6 fellows here, then you go into K naught, as was just pointed out. Thanks. Yeah. So that's the partition on the K side. We'll similarly have a partition on the L side. So 1, 2, 3, for instance, overlaps with 1, 2 at 2 elements. In fact, 1, 2, 4, 1, 2, 5, 1, 2, 6, they all overlap with K naught at 2 elements. So all of those guys go into L2. 1, 3, 4, 1, 3, 5, 1, 3, 6, and so on, overlaps with 1, 2 at exactly one element, so they all go into L1. And then you're going to have a bunch of 3 element sets that don't overlap with 1, 2 at all, and they all go into L0, right? So that's this partition. Like I said, it's mildly annoying that we're using the same notation, and I was also kind of too lazy to change it, so this is what we have right now. So yeah, this is a partition of the K space and the L space. And notice that all of these paths are actually going to be non-empty. And part of the reason for that is because K and L are both at most n by 2. It's possible that, for instance, if because K plus L are both at most n by 2, K plus L is going to be at most n. If K plus L was greater than n, then some of these paths would be, for example, if K plus L is bigger than n, then L naught, for instance, would have been empty, because if you have to avoid all of K naught and be a L size set, but K plus L is greater than n, then there's no way to do that, right? So it wouldn't have fit. But for now, all of these paths are actually non-empty because of our choice of K and L being at most n by 2. Okay. Is the definition of these parts of this partition kind of clear? Give me a +1 if the definition is okay. All right, thanks. Okay, then. So now it turns out that now we are going to do homogeneity in a different direction from what we have seen. So the claim is that if you look at any K and Ki, right, they have the same number of neighbors in Lj, and this is true for any Imj. And well, why is that? Well, fix the K and Ki. So this fellow overlaps with, maybe I'm going to try and draw this. Is going to be a disaster. So here's your K naught. And if you're in fancy Ki, that means that you overlap with K naught at some I vertices, right? And now I'm looking for, things that are sitting, things that we are adjacent to in Lj. But what is Lj collecting? Lj is collecting things that overlap with K naught at J things, right? So what if, okay, so let's see. What if J is smaller than I? So I am right now, I am somebody sitting in, so I'm a set in Ki, fancy Ki. I'm a set in fancy Ki, which means that I overlap with K naught at I elements. And I'm looking for all of my supersets which overlap. So in fact, let me make this explicit. and say, oops, erase everything, but I'll try and bring this back. So I'm somebody sitting in, let's say, fancy K3, right? That means that I overlap with K0 at 3 elements. Now, how many neighbors do I have in, say, L2? L2 is all of these sets with L elements that overlap with K0 in 2 elements, but now L also has to be a superset of K. So do I have any neighbors in L2? So remember, I'm counting. Okay, so I'm trying to count how many neighbors, like if I'm in K3, if I'm somebody in K3, how many elements of L2 am I seeing? Now, what is L2? These are all L-sized sets, which overlap with K0 at only 2 elements. I already overlap with K0 at 3 elements, and I want a superset of mine that overlaps with K0 at 2 elements. Is that possible?
I have a feeling
that I may have lost.
Most of the audience is lost, I think.
Okay, so let me see if I can just write out what I said, because this is like just a useful special case to think about. So I'm a set A in K3, which means that A overlaps with K0 at 3 elements. Now I want to know, is there a B in L2 such that we should. Okay, so hopefully this setting is clear. And now what's the other question I want to ask is that, is there a B in L2 that is adjacent to A? What does that mean? If I have to be adjacent to A, in other words, B is a superset of A, but it's in L2, so B overlaps with K0 at 2 elements. So are these two conditions simultaneously realizable? So just think of this as, even if the rest of the context is completely if the rest of the context doesn't make sense, just think of this as an independent set question about sets. So I have a set A which overlaps with some set K0 at 3 elements, and I'm trying to find a superset of A that overlaps with K0 at 2 elements. Is that possible? Yeah, no, right. So B is a subset of A. B is actually a superset of A, because B is in the L space, it's in the big space, and A is in the K space, which is the small space, right? So now I have a relationship with A based on containment. So A is a subset of B rather than the other way around. So Jayati, does that make sense? And Krishna just said no. And indeed, the answer is no, is because if I'm a subset, yes, if I'm a superset of A, I'm already committed to keeping everything that A has. Now, A already overlaps with K0 at 3 elements. So I cannot overlap with K0 at 2 elements unless there was a notion of overlapping that was negative, but there is no negative overlapping. So I can only pick up more elements, but I cannot pick up less, right? So yeah, so basically, if J is smaller than I, then Dij is basically 0. That I don't have any neighbors in the LJs where the J is smaller than the Ki's, right? So the only hope is if you're bigger, right, then there might be something going on. So if I'm bigger, then let's say that, I'm thinking about overlaps with, let's say, L5 or something. That means that I'm looking at all L-size sets that pick 5 elements from K0 and a superset of me. And this I can sort of count, right? But the important thing is that the count is independent of the exact place of the overlap, right? So no matter which set I pick in Ki is some set that overlaps at I elements, and I want to count how many supersets of size L are there. supersets of mine of size L are there, which overlap at K naught at some J elements, where J is at least I. If you think about it a little bit, you can actually count these sets, and that count will turn out to be the same for all elements in Ki, because it's really just about counting the number of ways that you can choose things from K naught minus the current set that we are focused on, and the number of ways in which you can expand to the remaining number of elements from the outer region of the universe. So you'd have to pick some stuff from outside to pad up this K size set to L size set. So you'll have to pick some extra from here so that you get the intersection size that you want. And then you might still have some budget remaining for extra elements. So you pick some from outside. But whatever that count is, it's independent of the size K. It's independent of the set K. All that we need is K overlaps with K naught at exactly I elements. But no matter how that overlap is, you will end up getting the same count. So this may be a little bit to fully be convinced about, but the important thing is that if J is smaller than I, then Dij is 0. If J is at least I, then you get some count, and it's a uniform count for for all sets in a common equivalence class Ki. You basically get the same count. So if you look at this matrix D, it turns out that so the Dij's now form a, if you like, a R by S matrix, right? So the Dij's turn out to be an upper triangular matrix, because we have shown that the lower triangular entries is 0 because of the way these intersections work, right? So yeah, if J is smaller than I, then Dij is 0. So this is an upper triangular matrix. We can also check that Dii is not 0, because that means that you want to maintain the same intersection and extend, which you can always do, right? So the diagonals are non-zero. So D is a non-singular matrix. Now we are going to basically use Y to produce an X which contradicts the non-singularity of D. That's how the proof goes. I realize I'm, well over even now the 1 hour mark. So I don't think I will drag this out much longer, except to say that the xi is the x vector is defined fairly naturally. What you do is to go from the y vector. Remember, the y vector was this big vector with n choose k entries, and to get a vector which is now only S entries or whatever, you look at all of these, in fact, not S entries, sorry, only K entries, because the Dij is here. This is a K by K matrix that we're talking about. So to get from Y to get to an X, which is a K or K plus 1 length, a vector with K plus 1 coordinates, what you do is basically you look at all the sets that are in the same part of this partition, right? And you basically take those Y values and you add them up. That's how you define X based on Y. And you do this with the K paths. And this is also because you know that Xi is non-zero, because you had a K naught in KK, right? The set which overlapped with K naught at K elements, that was that was just the set K naught, and we know that YK naught is 0. So this is a non-zero vector X that you've gotten out of Y, and then it's just like really a calculation. I mean, there isn't anything deep going on here. You claim that D takes X to 0, even though X is non-zero, and to argue that you just in fact, I found it more convenient to go at this from right to left, but you do the natural expansions and things work out. So this part of the argument is kind of routine. I think the cleverness is in kind of, actually, I don't know, maybe the whole thing is kind of clever, and there are a few moving parts. So yeah, apologies if things were a little bit unclear on the side. I think if I had spent a little more time, I think I would have tried to add more examples to the slides, but instead I was kind of fumbling with just giving you some on the fly. But I don't know, hopefully some of the main ideas come through in terms of, so surprisingly, the miniature, there's some trivia about how this has been a really hard theorem to prove. And some of the other proofs in the literature apparently throw in much more sophisticated machinery at this problem. And given the very combinatorial sounding nature of the result, you would expect there to be a counting-based argument, but apparently all of the arguments are kind of like this indirect. Apparently there isn't a first principles counting argument. He does say that you would expect that maybe you look at all possible ways of building walls with L bricks and all possible ways of building walls with K bricks, and maybe you show an injection from the latter to the former to say that the former is at least as big as the latter, but nobody has been able to apparently demonstrate a clean injection like this one. There isn't a direct combinatorial proof, and so we fall back on the magic of linear algebra or other tools. So apparently all the other proofs are also kind of a little bit left field, I guess, but use more machinery. So compared to that, apparently this is a relatively cleaner approach. And I think, as is typical of many of the miniatures, it's just I don't think there's a lot of intuition, but hopefully we get to a point where we are at least convinced of the mechanics of it, and the intuition builds over time somehow, one would hope. Yeah, so that's the end of my rambling for today. I'm going to pause here and invite any questions or comments, and then we can call it a day. So
yeah, so maybe I should say something.
yes.
I think the nature of miniatures have changed probably, since 22 maybe. I think the matrix tree theorem that we looked at, that was 21, I guess. Until that point, I think all the miniatures were really miniatures. This looks more like work. It doesn't seem to be fun anymore. So yeah. I don't know if other people will agree with me. I think we should ask. Yeah, okay. That is one. Yeah, okay. So
that will smile. No, I mean, I tend to agree that definitely. So I just wanted to say quickly that coincidentally, I was looking at the reviews of the book on Amazon, I think Amazon.com. And one of the reviewers said that, it was fun until miniature number 22, and then I stopped reading. So I think they found the same.
For 22, is it? Same number?
Yeah, same number. So until 22, it was fun and games. And then it sort of got... I suppose a little more intense. And
see, yesterday's thing, of course, is a classic result, but there wasn't much linear algebra at the end, right? It's really a combinatorial stuff.
True. Yeah, it mostly leveraged.
So I mean, that I don't know why it made it to the miniature at all. But until 21, I can see things. Mm-hmm. Beyond 21, this I mean, I don't know. Maybe he found it difficult. I don't know. Maybe he wanted 33 for some reason. I don't know. So, so maybe 21 would have been too little, or publisher would have rejected it. I don't know what it was.
Yeah, no, I mean, it's interesting you mention it, because I think I'm also finding it, slightly more uphill slope in terms of parsing some of the details. And also, I should say that just to make sure that we don't go on forever, or that I don't have to split it into two parts, I did not tell you about a lot of things that are there in the miniature, but most of that is setting a broader context, talking about, partitions and other things. And same for yesterday. I think even with the signed question, I think there's a lot of additional context. Maybe not a lot of it, but yeah, there's some additional context that I happily swallowed and didn't talk about, just to keep the presentation a little bit contained. And we're still going somewhat over time relative to our original goal of doing these half-an-hour sessions. I think that was out of the window a while ago already, but yeah, I mean, I don't know if anybody has any comments on like how they're finding this. It's also possible that my given that there's more to go over, but I'm not spending more time, proportionately more time in preparing the slides. So I think what's also happening is that, basically the slides are also a bit lazy. And maybe that's also a part of why maybe that they're appearing. The presentations getting a little more terse from my end as well, conceivably, because previously I think I was able to sneak in a few more examples and things like that. And now I'm waving my hands a lot more. So it's that it could also be a function of that. And like I said, I think I'm going to blame the material for becoming a little more intense as we are going along. I will say that in terms of what's coming up, most of the other ones are like this. They tend to be slightly longer stories. So they're not many miniatures anymore. And some of them are, well, there's definitely a couple of extremal set theory results coming up. There's a couple of pretty heavy geometry results, and then there's also I think again there's more graph theory as well. So we've just crossed the 2/3 mark yesterday, and now that we're done with this, we have about 10 left. If you folks feel like you need a breather, I'm happy to also sort of, take a longish break here, considering we are heading into December, and that's probably holiday / travel / exam season for some of us. So if it makes sense, happy to take a collective break and try to do a reunion set of meetings, maybe in Jan or something like this. I don't know if that's a nice way to ring in the new year, but that's a possibility. So those of you who have been kind of long-standing sufferers are actually here right now. Do you have any comments on how do you want to steer this? I mean, I'm happy to also just carry on, but if anybody would want to vote or suggest something, I'm all ears, basically.
So we seem to have lost two of our regulars, right? Or maybe
I think,
more.
I mean, I know that Janki and Joel, and I think a couple of others used to.
I think Manu, I thought he was there, but he doesn't seem to be here.
Right. I think Manu joined at the start. I think has dropped off for a bit, and
Jagdish, I guess.
And Jagdish, yes. And possibly a few others. So yeah, and I think Jayadi, I don't remember if it was you who earlier said that you're also okay with the longer session. So I really admire your flexibility with all this. So thanks a lot. Okay, all right. Yeah, thanks, Pradesh. It's good to have you on board. Good to see you. And yeah, it'll be great if if you happen to be around, and it'll be fun to continue doing this. Yeah, I think that's totally fair. I think if a session goes way over time, I think, it totally makes sense if you need to drop off. Yeah, I don't know how much confidence I have in so for me, I think I've seen these miniatures on and off here and there, that sort of thing. And as you can probably tell, linear algebra isn't really, unfortunately, I don't have a chance to use it in my regular work. So I don't really know it very well or even at all. So I thought this was a great excuse to try and pick up some. So you're also suffering through, my learning process and kind of being exposed to that as well. So, but if you're up for it, I think there's definitely 4 miniatures that I suspect are kind of lengthy, and I will probably make the choice of breaking it up instead of trying to squeeze it all in. These are things to do with, I think, so I think there's something called the Shannon capacity or something like this that comes up. And the last 2 miniatures are kind of conceptually also kind of a little bit heavier than typical. So there are these 2 related miniatures about graphs where the Shannon business comes up, those 2 and the last 2. So there I expect things to spill over. So maybe we can put those kind of, I don't know, we'll figure it out. But the others, I'm hoping I can still continue doing them one at a time. And hopefully we won't lose too many people as we go along. And and hopefully some of our regulars are back as well. So, okay, so let's maybe meet tomorrow. It's not calling a grand pause on this just yet. But Vinay, did you have any other?
I think tomorrow should be fine. Tomorrow, I think.
Yeah, tomorrow we'll pick up again the permanent.
Is central to whatever theoretical computer science.
Yeah. It is, yeah, and it would be a little sad if I managed to screw that one up. So tomorrow should hopefully be okay, and then yeah, if anybody does, I mean, please feel free to be vocal. I know it's super sweet of all of you to tag along this journey, and we should be done in just a bit. But yeah, if we're certainly open to exploring other formats or other timings or whatever. So yeah, if you have any suggestions, so if you want to make them,
Yeah, so let's finish this week and see where we are, no? On maybe Friday
yeah,
or something, and
yeah,
we can
maybe
take a call on Friday.
that sounds like a plan. And in the meantime, yeah, if you have thoughts that you want to share separately, feel free to send me an email or whatever. So, all right. So then I think this is a good place to stop. Thanks so much, everyone. And see you back tomorrow, 10 p.m. And we'll do permanence determinants again, I think. And until then, goodbye. Good night.